Today, a linear functional will stop being a mysterious scalar machine and become inner product with one vector. Very tidy. Suspiciously tidy. The punchline is that, in finite dimensions, every linear functional is secretly taking an inner product with a fixed vector. First, recall the definition. A linear functional is just a linear map whose output is a scalar. The codomain is the field. Real numbers for real vector spaces. Complex numbers for complex vector spaces. Linearity means it respects addition and scalar multiplication. No drama, just the usual contract. Coordinate extraction and integration are examples. They output scalars, not vectors, because apparently one kind of object was not enough. Now assume V is a finite-dimensional inner product space over the real or complex numbers. Then every linear functional has a unique representing vector y, meaning phi of u equals the inner product of u with y. We keep the same convention as before. The inner product is linear in the first slot. This matters in the complex case, because conjugates are petty but necessary. If phi is the zero functional, the representing vector is 0. So suppose phi is not 0. The null space U of phi is a hyperplane. It has dimension 1 less than V. A fancy word for almost everything, mathematically speaking. From the orthogonal complement theorem, V splits as U plus U perp. Since U has codimension 1, U perp is one-dimensional. Choose a non-zero vector W in U perp. Because W is not in the null space of phi, phi of W is not 0, so we can divide by it, a rare moment where division behaves itself. For any U, subtract the right multiple of W so phi becomes 0. That vector lands in U. Since W is orthogonal to all of U, the inner product of that vector with W is 0. Solving that equation gives a direct relationship between phi of U and the inner product of U with W. Define Y to be conjugate phi of W divided by the square length of W, times W. Then inner product with Y gives exactly phi of U. The conjugate appears because the scalar is in the second slot. Complex numbers. Forever billing us for bookkeeping. Now suppose two vectors represent the same functional. Uniqueness is where positive definiteness quietly does the dirty work. Subtract the two equations. The difference vector has inner product 0 with every U. Now choose U to be the difference vector itself. Its length squared is 0. Therefore the two representing vectors are the same. Existence and uniqueness are both done. Now we use the representation theorem to define the adjoint of a linear map. Let T be a linear map from V to W. Fix a vector W in W. The map sending V to inner product of TV with W is a linear functional on V. By the representation theorem, there is a unique vector called T star W that represents this functional. This equation defines the adjoint T star. Well-defined means two things here. Each W gives exactly one vector T star W, and the resulting map is linear. Existence and uniqueness come directly from the theorem we just proved. We are not choosing randomly. For once. For linearity, test both candidates by taking inner products with an arbitrary vector v. The conjugates are exactly what second slot conjugate linearity demands. By uniqueness of representing vectors, those two vectors must be equal. So T star is a well-defined linear map from W back to V. A linear functional is scalar valued, but in finite-dimensional inner product spaces it is represented by a vector. That representation makes the adjoint possible. Next, the adjoint starts doing actual work. Null spaces, ranges, and eventually the matrix formula. Linear algebra loves saving its nastiest tricks for after definitions.